before we start, just a quick announcement about the conference dinner on Thursday night. The sign-up sheet is there. So if you're coming and you're bringing accompanying family member or whatever, please indicate how many of you are coming on that sheet. And please do it before lunch, because we have to hand in the names of this applicant. Excellent. Just up there at the front, right after this talk, if you haven't already done so. So it's a pleasure to have Barbara Fantechi here, who will tell us about Lagrangian subspaces and moduli of those over a K3 surface.
Thank you very much for having me here. This is a report on joint work with Rosa Maria Miro-Roy, and is on archive this year. I don't remember the number, but I don't think if you search my name and her name, we have only 2 papers and only one has Lagrangian in the title. And so what is this about? So I'm going back to this morning, to the first talk. Remember, you all know that if M is a manifold, you know what it means that it's symplectic, and you know what it means for a submanifold to be Lagrangian. And what I want to work on today is the complex holomorphic version of all of these. So M will be a complex manifold, which will be complex or holomorphic symplectic. And so our 2 form will have only DZs and not DZ bars, and the coefficients will be holomorphic forms, but it still has to be closed. And then our L will be a complex submanifold. And, well, Lagrangian is the usual definition of half dimension of a half complex dimension. And so our goal today is construct examples of pairs like this, where M is compact. So the point is, in holomorphic geometry, compactness is very, very strong requirement. In particular, because holomorphic functions on a compact manifold without boundary must be constant by the maximum principle. It means these can never, real manifolds all embed in Rn, but compact complex manifolds, all the maps to C, holomorphic maps to C to the n are constant. So the next best place you can put them in is projective space, because there at least you can. So we will always be interested in projective complex manifolds, and they are just compact. And so in particular, closed. When I say manifold, I never have a boundary in some projective n space. And in fact, I am an algebraic geometer. And why am I talking to you about complex geometry? Because in this situation, there is something called Gaga principle, where Gaga means algebraic geometry and analytic geometry, but in French. And so Gaga principle means that, in fact, first of all, algebraic submanifolds of Pn are the same, just the same thing as holomorphic submanifolds. So basically what this means is that they are actually defined by zero locus of homogeneous polynomial. And so I can work using algebra. I don't need whole or holomorphic functions. I can work on them using polynomials and ratios of polynomials. And the other thing is that vector bundles here are the same as vector bundles here, and they have the same cohomology groups. Even though on this side, typically I will think of cohomology groups by Dolbeau cohomology, and on this side I think of cohomology groups using Schiff cohomology. But the result is absolutely the same. So this means that I thought that we work on the whole thing on this side, but what we did works exactly unchanged on the other side, and in fact, at some critical point, we had to cross the barrier and use complex analysis to prove the key result, not just the one lemma. Okay, so this, and so if you want to find such examples, in fact, already the example of compact, complex, holomorphic symplectic space are not so many. So already M has not many examples. And in fact, the let me start with a very basic example. So what is the smallest reasonable example? Of course, I have to have something of even dimension over the complex numbers. So the basic example, you can have one of them is T2, a complex 2 torus, well, assuming it's projective, which it isn't always. So this means you take S1 to the 4th and you give it a complex structure such that it is projective. And this is, the point is this you can also write as a C2 modulo some lattice. And this means that you just take the usual, you view C2 as the cotangent space to C1, and you have the usual form, and it's invariant under the translation by the lattice. And the second example, you see here, if you just take coordinates P and Q on CQ, here the invariant differential form is dP wedge dQ. So it's also invariant under changing sign at both P and Q, because if you send PQ to minus P minus Q, this does not change. And so what you can do, and as was explained before, this you get some singularity, and you get singularities at the fixed points, which are 16. You get 16 singular points, and it still has a natural, and in fact unique, complex symplectic resolution. And this resolution is called a Kummer surface, and more generally the same. Any surface, remember it's a form manifold, but I think of it as a surface, and it has many more complex structures, and any of them is called K3 surface. So the idea is you have this C-infinity structure and you take all the possible holomorphic, this is 20 dimension, and the projective ones are 19 dimensional. So like for torus, it has 4 complex moduli. Moduli means possible holomorphic structures on a given C-infinity structure. And this is 4, of which 3 projective, and this is 20, of which 19 projective. And Actually, let me say that there is an even more basic examples to show you how mathematicians think. So, more basic example is I take M is 1 point, and L is also 1 point. I mean, on M, you take the zero differential form. It's still non-degenerate because the tangent space also has dimension 0. And 1 point has dimension 0. What is the half of 0? It's also 0. Now, you may think this is insane, but I promise you this is going to come back. Okay, so these are the basic examples. As I said, there aren't very many. And a classical one is the fact that for any x projective K3 surface, and in fact, for the rest of the talk, we will fix an x projective K3 surface, which means we take this differentiable structure and we fix a holomorphic structure in such a way that it has some embedding in a projective space. And any choice of rank and Chern classes, the moduli space of stable sheaves of given rank stable coherent sheaves on X of given rank and Chern classes. You should think coherent sheaves. If you don't know, it's like they try to be a vector bundle, but it's algebraic geometry, so some of them come out a bit wonky. And so they have, a vector bundle means for every point you give a vector space. Coherent sheaf is the same thing, but some of these spaces jump dimension. Think of it, you have a linear map between vector bundles, and you take fiber-wise the kernel. What you will get is that most of them will have the same rank, but some of them will be bigger. And this is what you should think of it. And the stability is a condition that can be defined algebraically, and I'm not going to do that. But for vector bundles, it can also be defined in terms of choosing a metric and having certain good properties in how the metric relates to the complex holomorphic structure. And this is complex symplectic. This is due to Mukai. And under good assumptions, under extra but not very restrictive assumptions, it is also compact and in fact projective. So our goal would be to produce Lagrangians inside here. However, it turns out this is at the same time too big and too small. Too big because this means we have to work with coherent sheaves, and in fact our construction only works with bundles, which actually makes it easier to understand. But at the same time, it's too small because checking stability is not so easy. So if you produce a bundle, to show whether it's stable is not an obvious statement. So instead of working with this, we work with something which we call in this way, and instead of stable, we take simple, but on the other hand, instead of coherent sheaves, we take vector bundles. And the simple has a much, as the name says, is a much simpler meaning. E vector bundle is simple if the only holomorphic maps are constants. So of course, if I have a holomorphic bundles multiplying by a global scalar is a holomorphic map, and there are no others. In other words, it's H0, the global sections of the endomorphisms are just the constant functions. And this is also complex symplectic. In fact, they both have a common generalization because you can define being simple also for coherent sheaves with the same definition, and then you can prove it's pretty elementary that stable implies simple. And so what we do is we work with this, and we hope that these two will intersect non-empty. And once we have a non-empty intersection, we use the power that we are here, and we have that the intersection is a very big open dense subset. And so, by the way, if you remember, there was a discussion, do we need things to be non-singular to be Lagrangian? And this depends, you know, on you. So typically, if you have M projective, and you take any Y inside M subvariety, and when I talk about subvariety, it's not because I'm thinking in Italian, where variety and manifold are the same word, but because it could be, say, singular, something like this. This is not a manifold here. But so how do I define whether such a thing is Lagrangian or not? What I do is I just remove the offending point, and then I'm left with a manifold. And so what I do is I allow my submanifolds, I will always mean locally closed. And locally closed basically means that every point has an open neighborhood where it's a closed submanifold. But I don't have global assumptions. But I want that it's locally closed in the algebraic sense. Our construction provides this, and then you get automatically that the closure is considered Lagrangian. So the way algebraic geometers define Lagrangian for singular stuff is, say, ignore the singularities. And so now our goal goes as follows, is we provide two constructions that do the following. You start with a Lagrangian inside one of these spaces, so a space of bundles, and you find a machinery that will give you another Lagrangian in a different space. Why did I mention the nonsense about the point? Because if you wonder, okay, you have a construction that it's a Lagrangian and outputs a Lagrangian, it's fine, but where do you start? Where do you get the Lagrangian to start with? And the answer is, for instance, if I choose the rank is 1 and C2 is equal to 0, then it turns out that SPL are 1, C1, 0, either is empty, but if it's not empty, it's 1 point. It's just the class of one line bundle. So vector bundle, holomorphic vector bundle of rank 1. And then you can view this point as Lagrangian, apply this construction, and get a honest-to-God positive dimensional Lagrangian in a honest positive dimensional space. So you start with nothing, and you create stuff out of the weird examples. So this is in brackets. So let me start by saying how the first construction works. The first construction is a special case of a very classical construction in algebraic geometry, and it's called the generalized CZG bundles. Besides this, I think being the only word in the English language with two Y's and having a meaning in astronomy and also, as far as I know, in astrology, it's used in algebra to mean to find the relationship. So first I'll define you these bundles, and then it will be hopefully I will explain why they're called syzygies. So if you have F, a vector bundle on X, and you have V, vectors finite dimensional, it's always, everything will be finite dimensional, vector space of holomorphic sections, then what you can do is you get an induced natural map from the trivial bundle with fiber V to the bundle F that takes a pair, section, and point and maps it to the section computed in the point. And what I will assume is that this map is surjective. So assume surjective, and now you remember I told you if you take a kernel of a morphism of vector bundles in general you get something weird, but of course if this is surjective the rank is constant, and so the kernel, for some reason algebraic geometer defined the kernel by saying that this is an exact sequence, and this just means that this is this kernel and this is a vector bundle, and it's called syzygy or generalized syzygy because you see you have these relations, so in every point these sections are points in the same fiber, and these are the equations relating these points. So you have these sections and these bundles controls fiber-wise how these sections are related to each other, even though globally I am assuming that they are linearly independent, but of course, for instance, if my bundle is rank 2 and I have 5 sections, I expect point-wise to have 3 relationships. And it's called typically the original definition of syzygy bundles starts with all holomorphic sections, which have to be finite dimensional, and we weaken it to this case. For the case, this is very studied in algebraic geometry. You don't need X to be a K3 surface. In fact, the case where X is a projective curve has been studied extensively. And what we did with Rosa Maria is we studied the case where the dimension is 2 or higher. We proved that in dimension 3 and higher with some assumptions, the construction relates moduli of bundles to other moduli of bundles birationally, which means they are mostly the same up to a subset of dimension 0. But in dimension 2, this result is false, and there's plenty of counterexamples. And the first thing you remark, however, which is why we wanted to work with simple, is a lemma. And the lemma is that if F is simple and H1 of F, I think this is too many assumptions, but this is the assumptions we'll use, then E is also simple. So this is a way that inputs a vector bundle plus something, in this case a vector space of sections, and outputs another simple bundle. And so what we do now for any L in submanifold, here I don't need yet that it's Lagrangian, just a submanifold, I fix a dimension little w, well, it has to be at least 3. I can define, I should have this in the notation, but for simplicity I will assume it's fixed and ignore it. I define GL is the set of pairs, sorry, this is V, Fv, such that F is in L, it's a vector bundle after all, so this is the set of all simple bundles with a natural structure, so every point here is a point here, it's a vector bundle, such that H1 of F is H1 of F star. Actually, I would need both, but in fact, I need only one because these two are equivalent for K3 surfaces. And V is in H0 of F, has dimension V. And this has, of course, a natural map to L, which is you send Fv to F. And this is a Grassmann bundle over an open subset, a dense, an open subset. And so if everything is algebraic, this open subset is either empty or dense. So it means I keep most of my Lagrangian. And there are conditions. And then I can do G0 of L, which is the same, but now I add the condition that V times X to F is surjective. And this is open in here. Which also means Grassmann bundle means every fiber locally it's a product with a Grassmann complex manifold, which is after all projective manifold. And so if I assume that this was a submanifold, then this is also a manifold, and this is open in a manifold, so it's also a manifold. And now, of course, I have, so what I have a map from this to another space, well, where R prime is V minus R, because it's this sense F V to E. And if I do this construction, the rank of E is the dimension of V minus the rank of F, and you can compute the Chern classes. Explicitly. And what we prove is the following. So, of course, assuming in the following that, assume that G0L is non-empty. I mean, it's also true for empty, but in some sense, but it's not very interesting. Proposition 1. Notice that until here we didn't use that L is Lagrangian, just a submanifold, but we will move towards it. So first of all, the map beta is an embedding, which means that its image, it's a biholomorphism or diffeomorphism, which is complex holomorphic on both sides, with its image L prime, which is a submanifold. So at least I start with a submanifold, then I get a submanifold, which is a good start. And the second thing is that if the dimension of L is half the dimension of its moduli space, then, and in fact, if and only if the dimension of L prime is half of the dimension of its ambient moduli. So you have a machinery that inputs submanifolds of something which has a complex symplectic structures and outputs submanifolds and preserves having half dimension. And so now the question is, does this preserve being Lagrangian? And our theorem is indeed that, theorem, this L is Lagrangian if and only if L prime is Lagrangian. So this, again, this provides, it's a very natural construction, and it gives us, as an algebraic geometer, a very good control on the geometry on L prime in terms of the geometry of L. And so we really have a good understanding, and in particular, we get lots of examples in which L prime is what we call rational. Rational is the easiest version, the easiest to understand of any algebraic varieties. It means I can parameterize it by some, if it has dimension d, I can parameterize it with c to the d. It means it's isomorphic to c to the d up to throwing away stuff of dimension 0, which is nowhere dense. So a big chunk of it is a big chunk of c to the d. So this is nice. The bad side is, so future, hopefully, work, what we are struggling with it, is to check stability. And there is something we know for a fact, that if you start with a stable bundle, you do not always get a stable bundle. What seems more realistic is that under mild numerical assumptions, if the general element, so there is a in every case, stability is an open condition. So either most of elements in L are stable or none are. Most elements in L prime are stable or none are. So what we say in algebraic geometry language is the general element is stable, to mean most of them. And so what we think is true is under mild assumptions, general stability here will be equivalent to general stability here. But at the moment, we aren't there yet. We have a few, like hand-picked examples like flowers where we know how to do it, but we are far from a general statement. And on the other hand, we have extremely far-reaching counterexamples that show that even you start with something where everything is stable, you do not expect here that everything is stable. So if you want to understand a little bit what is going on, what is going on kind of under the hood, what I am hiding from you. So, hidden knowledge, so that you get some familiarity with what we are secretly doing, is that, in fact, the theorem of Mukai applies to simple, coherent sheaves. This Mukai shows that this is a complex, symplectic, it doesn't say complex because it's smooth algebraic space. So this is the language in algebraic geometry. Let me translate it for you in terms of manifolds, but before I do that, it contains as open both simple bundles, vector bundles, and stable coherent sheaves. And now, if you have some familiarity with the notion of compactness, you know that one of the first things you prove is that if something is compact inside something else, is closed. So how does this stay here and instead of being closed is open? What's going on? And let me make a drawing. This is not the drawing of the actual moduli because this is very big. So I will pretend that the moduli is one real dimension. What you should be thinking of is that not only, you see, this would be something compact. Think of this. This is S1 and it's compact. And the simple coherent sheaves is just you take your S1 and then you glue another, you take two S1s, say on two different planes, and then you glue them all for Z different from 1. So you should think you have these two circles and you glue them all except in one point. You get something which is like a manifold, but it's not Hausdorff. Because if you take a sequence that goes to this point, it has two limits and not one. And what happens on this other side, so here you have thrown away the stuff which is not stable, and it means you exactly, kind of for every multiple possible limit, you chose exactly one. And on the other side, instead, you have a much easier condition because you can look at the one of these weird things and check is a bundle by just looking at the dimensions. But in this case, you are also throwing something away, but what you're throwing away is no longer good. And so what you get is something like this. So it still has the weirdness, and moreover, even if you get rid of it, it's no longer compact because you are missing the coherent sheaves. So in fact, we are working with this, and if I have to be even more honest, we are actually working with algebraic stacks. So we are doing something a little bit more exoteric, which means basically it means we are assuming that we have universal families on these moduli of bundles. The point is you can do all the calculation with the stacks, and then you just hide them out in the statement of the theorem. The stacks are there, but they are hidden in the proof. They are not in the statement. And I promised you two constructions. So what is the other? Well, you look at this construction, and it says, basically what we are assuming is that the relation between our two bundles are related because they are in this short exact sequence where the third term is a trivial bundle. And so the construction 2 is we try to do something similar, but we change the place where the trivial bundle is. So we study this case. And now there isn't an obvious way to study this. So if I give you F and W, what information do I need so that I get such a sequence, so that I get a vector bundle surjecting on F such that the kernel is naturally this trivial bundle? And the answer is this is equivalent to saying that W star is contained in H1 of F star. And we have that E is simple if F is simple and H0 of F is H0 of F star is 0. So it means F has no section and his dual also has no sections. So this looks like a bit more delicate condition. It basically is never true for line bundles, so our silly example doesn't apply, but we can use the silly example to produce a non-trivial one, and then this will apply. And in particular, this condition is true if F is stable with C1 of F is equal to 0. So it's not the empty condition, let's say. And of course, rank bigger than 0, bigger than 1. Okay, and then we can do the same. Again, we take an L inside SPL R C1, C2. Now the Chern classes are even easier to compute. It's R prime is R plus W, where W is the dimension of this space, and the CIs are CI primes. CI are the rank of E is the rank, and the CI of E is CI of F. And so we take the set of such pairs, W, F, with, again, F, H0, F is H2, F, and F is in L, and we call it PL, and W star contained H0, F star. It's the same thing, but I want to be consistent, is dimension W. Notice that in this case, we have a somewhat more, reasonably more special conditions, but we get a better result. This is now a projective bundle, a Grassmann bundle, but we don't have to throw away anything. It's a whole Grassmann bundle, and you can copy the same result. So you have the lemma, and notice that this really works. The previous construction works over an arbitrary base, but this is pretty much about K3 surfaces. The lemma is that, yeah, it's E is simple. And then we have a proposition. So again, we give names to this. We consider the map for any L in SPL R CI submanifold, sending F W to E defines a map beta from PL to SPL R plus W CI, and the theorem is exactly the same. That this, first we prove it's an embedding, then we prove it preserves being half-dimensional, and finally we prove it's Lagrangian. So this is what we do, and since I have still a few minutes, I would like to say something about the proof. And the point is, you may wonder why something a lemma, something a proposition, and something a theorem. And of course, the answer is it depends on how long the authors had to struggle to prove it. So the lemma is actually, as I said, the lemma and the first part of the proposition are true in very big generality for construction 1. You really just need it's a surface, a smooth projective surface, plus the fact that this thing is non-empty at all. The proof of the lemma and the first part of the proposition for K3 surfaces is about the same difficulty in that once we have done it, we can copy the argument. And finally, the dimension count is pretty easy because we have an understanding of what the dimensions are. Remember, this is a Grassmann bundle, so we know, given the dimension of the basis, what is the total dimension. And on the other hand, we can, the dimension of these moduli of simple bundles is very easy to compute. It's the tangent space is H1 of the endomorphisms of E. This is actually something that I think was first proven in complex geometry. So you really have a Kodaira-Spencer type of deformation. And you just compute, sit down, and then a miracle occurs, a number of things cancels, and you get this half. And the part which took us a bit longer, or rather quite a bit longer, was the Lagrangian part. And let me describe for you how the proof goes. For construction 1. Funnily enough, it turns out that the case of construction 2 is significantly easier. It's the same idea, but easier. So I'll focus on the construction 1. And for construction 1, it goes as follows. Remember, you have your G0L. So this is this set of pairs F and V with some properties. And it has two maps, beta to this new moduli, which sense is given by the bundle E. And it has a forgetful map back to SPL RCI, which is, in fact, goes to L, but a priori is given here. And these are the maps. And what we want to prove is that alpha pullback of the dualizing of the symplectic form is a beta pullback of the symplectic form. This is symplectic, it has a form omega. This is symplectic, it has a form omega prime. If you prove that the two pullbacks are the same, then they are, you see, since remember, these factors as a smooth, as submersion here, and this goes into then you have that the restriction omega restricted to L is 0 if and only if the pullback of omega is 0, because this is a surjective on tangent spaces. And what we do is we take, now here we are really doing algebraic geometry for a minute. We take a different space where we don't only fix F and V, but we choose a basis for V. And it turns out that what we get is something called the quad scheme of OX to the direct sum V. And this has a projection. It's not the whole quad scheme, it's just a part, but we can work with the whole quad. And this is again a smooth, a surjective submersion. And so to prove this equality is enough to prove this equality. And now we have to use who are to, you have two forms. To check that two differential forms are the same, it's enough to check on every tangent space. So what are the tangent spaces? It turns out the tangent to SPL is H1 of the endomorphisms of F. The tangent to the other one is H1 of the endomorphisms of E. And the tangent to quat is H0, or if you want, it's HOM E F. So how do you give these maps? And you look back to our original exact sequence. And this defines for you a class E in H1 of F dual, F tensor, okay, now I have to get it right, F dual, H1 of F dual tensor E. And so what we did is we viewed this as a Dolbeau form of the form sum of alpha of lambda I dzi bar, where the lambda i's are local maps from F to E. And now if here I have a map in this way, how do I go from here to here? And from here to here, I send phi to, you see, phi goes from E to F, so I have a phi here and a phi here. And so I can compose two different ways. In this way, this is sum of phi composed Li dzi bar. And in this way, it's sum of lambda I composed phi dzi bars. And then you do an explicit calculation with differential forms. I mean, there is some steps, because of course now you also have to use who is the Mukai form. The Mukai form can be again written in terms of composing endomorphisms and taking traces. And you show that the two results differ only by a sign. And as I said, there is a similar idea in the construction 2 case, but it's much more straightforward and you don't need differential forms like this. It's a consequence of a more general result, more straightforward result about bundles. Okay, thank you so much.
There's a nice construction of Lagrangian in this moduli by Turing, where you assume that your K3 sits as the anti-canonical class in the panel, and then you look at the subspace of like the moduli of those bundles that extends to the panel, maybe with some homological restriction like H2 is 0 or something like this. Does it fit in your framework?
I wish it did, but it would require some work. So the point is, this is really what I think of as a Turing's dream. Because of course, the one of the standard ways to think of, remember, when we want to do this critical loci, one way to get a critical locus is to intersect two Lagrangian inside a symplectic moduli space. And so a very cherished idea due to Turing, who unfortunately passed away untimely 21 years ago, almost, was that usually you think of these as bundles on a Calabi-Yau threefold, but if we degenerate, we can think of our Calabi-Yau threefolds as two threefolds, two funnels, meeting transversally along a K3. And then we have exactly two Lagrangians, in each case. And I don't know, actually. This is a very interesting question. So, again, I remember that back in the day, the problem with Turing's construction was precisely that it was hard to push it on the boundary. So that it worked well so long as you stayed with bundles. And when you started to go towards coherent sheaves, it became a bit more problematic. And if you want my honest opinion, what one should combine is this dream with a different dream by a different, unfortunately passed away mathematician, who is Trautmann. And his idea was that if I take a smooth surface, I normally compactify bundles by allowing coherent sheaves, but I could also compactify them by adding bundles on kind of extensions of the surface. So instead, basically, when I have a bad point, I blow it up. Blow up is something algebraic geometers do whenever they are disturbed. And you can get something with all bundles, and then one could do Turing's construction on the nose. But I don't know anybody that has done that. I think that would be actually amazing.